Alright, Assalamu alaikum. This is Talha bin Nadeem, and this is the fourth video tutorial of the topic mechanical injection system. Um, in the last video tutorial, we basically started off our topic with the fuel feed pump, and we studied about the how these fuel feed pumps work, and then we discussed about the injection pumps, that what are the injection pumps and how do they operate. We also discussed the two different types of the injection pump. First one was the jerk type pump, and the second one was the distributor type pump. And we also discussed about the working principle of these two pumps. And not only that, we discussed the details, but I have also shown the videos of these two different type of injection pumps, uh, and those animations were were giving a very good idea regarding how these different types of the pumps would be operating. So now today I am going to start off with the with another topic, with the next topic of this chapter of mechanical injection system. And as I mentioned you in the last video lectures, that we will discuss four different components of this injection system in quite some details. So far we have studied fuel feed pumps and the injection pumps. Now today we will start off with the third topic, and with the third very important component of the mechanical injection system, and that is of the governor. So as I mentioned in the earlier classes, in the earlier videos, that the purpose of the governors in the mechanical injection system is basically to control the speed, control the you can say control the amount of the fuel. And how do they control it? They basically control it by adjusting the rack, that combination of the rack and pinion, by either increasing the effective stroke length or either reducing the effective stroke length. That's how these governors basically control the amount of the fuel which is to be injected into the combustion chamber. So fuel delivered by a pump increases with the speed, whereas the opposite is true about the air intake. So it is mentioned here that when we increase the accelerator pedal in the CI engines, the amount of the fuel, basically the amount of the fuel, the more amount of the fuel would be injected into the combustion chamber, and the injection speeds and the fuel speeds of these fuel would also be increased. So at very high speeds we can often occur with the problem of overfueling, which can result into the incomplete combustion, and thus giving us some undesirable gases in the output as well. So this results in overfueling at higher speeds and at idling speeds. The engine tends to stall due to insufficiency of fuel. Similarly, at higher speeds, we would have a problem of the overfueling, but at the lower speeds we can have a problem. The engine may stall because of the lesser because a smaller amount of the fuels are being injected. So the quantity of a fuel delivered increases with the load, causing excessive carbon deposit. That's the environmental effect which I was mentioning, that when at higher loads more amount of the fuel is being injected into the combustion chamber, which can result into the incomplete combustion, thus giving us excessive carbon deposits and high exhaust temperatures as well. So similarly, when a sudden reduction in the load may cause the overspeeding in the engine as well, which can even lead to the engine failures. So these conditions are also being encountered by using the injection pumps, injection pump governors of the injection pump. So it is the duty of the injection pump governor to take care of the above limitations. So what are the limitations? At higher speeds, governor needs to take care of the overfueling phenomena. At lower speed, governor has to overcome the stalling problem, and then if the large amount of the fuel and similarly when a sudden load has been reduced suddenly, then it can lead to overspeeding of the engine and may result in the catastrophic failure as well. So governor has to overcome these problems, these conditions. We have two different types of a governor which are being most commonly used. First one is the mechanical governor, and the second one is the pneumatic governor. Okay, starting off with the mechanical governor. Here you can see, first of all, we must understand that what are the basic components. We have this spring, and this spring is connected with the centrifugal weights. Similarly, we have a sleeve here, and this sleeve would be either moving up or down. Then this lever is basically controlling the fuel rack, and this is the governor shaft. So what will happen here is that this when we are operating our engine at the higher speeds, or we can say that when the engine speed exceeds the limit, these fly weights, these centrifugal weights would be rotating, and because of this centrifugal forces, these weights will go against each other, and since they are for example this point, since it is moving because of the centrifugal force, it is moving in this direction, and this centrifugal weight is moving in the other direction, and because of the movement of these centrifugal weights, these joints will move away from the governor shaft as well because of the centrifugal forces. Similarly, this will also move in the other direction, and because since these levers are connected with the sleeve, the sleeve will move upward, and when the sleeve moves upward, it will operate this lever, and therefore the direction of the lever, the position of the lever would now be like this, and since because of the movement of this lever which is operating the control leg has now moved downward. So this is how the governors are operating, and they would be controlling the amount of the fuel which is to be injected into the combustion chamber. So when the engine speed tends to exceed the limit of the weights, these weights will move apart. This causes the bell crank lever to raise the sleeve. This is basically our bell crank lever. These levers which are connected to the sleeve. These weights will move away. These levers will move away from each other, and because of this movement, this sleeve will move upward. So and because of the movement of the sleeve in upward direction, the control lever will move in the downward direction. This actuates the control rack on the fuel injection pump in a direction which will reduce the amount of the fuel. So lesser amount of the fuel would now be delivered, which will cause the engine speed to decrease. And when the engine speed decreases, these flyweights which have moved away from each other will now come towards each other, since the engine is operating at lower speed and we now have a lower centrifugal forces. So this spring will bring back these centrifugal weights towards each other. So I hope it is clear. Now I will show you the video of the mechanical injection of the mechanical governors. Let's start.
For light automotive use, governors on inline pumps are usually mechanical or pneumatic.
Okay, so we have either two types of we have either a mechanical governor or a pneumatic governor. First of all, we will discuss the details of the mechanical governor. This is the typical arrangement of the mechanical governor. So in these slides, I have this governor is placed in vertical formation. However, in this video, the governor is in the horizontal. The shaft of the governor is placed horizontally. This is the sleeve. These are those counterweights, and this is the spring. Similarly, this is the control rack which is operating the fuel pumps, the amount of the fuel which is being injected into the combustion chamber.
A mechanical governor uses rotating flyweights to control movement of the fuel control rack against a spring.
Okay, so we have a rotating flyweights, or you can say a centrifugal weights, which are rotating, and with the rotation of these flyweights, this sleeve would be moving either up or down against this spring force, thus controlling the fuel rack. And this fuel rack would be controlling the amount of the fuel which is to be injected into the combustion chamber. Note that when we have applied a higher centrifugal force, or the engine is operating at the higher speeds, this sleeve will move downward. When the engine is operating at lower speed, this spring will push the sleeve back to its original position.
Removing the load from the engine lets its speed rise. Centrifugal force pushes out the weights, which push a sleeve against the spring. The force from the spring tries to push the rack to the maximum fuel position.
Okay, so as the engine speed rises, these flyweights will move apart. This sleeve will compress the spring. Sleeve is moving towards the spring against this spring force, and with the help of this lever, the control rack has been operated, and the desired amount of the fuel is then being injected by the pumps into the combustion chambers.
The force on the sleeve from the flyweights acts against the spring to try to push the rack to the minimum fuel position.
Okay, so centrifugal force is moving it in the right direction, and since we have this spring force, it is only moving in this direction, and whereas the control rack will move in the outward direction, thus controlling the amount of the fuel and injecting the desired amount of the fuel.
For any governor position, the fuel control rack determines the volume of fuel delivered and therefore engine speed. During idling, the governor prevents the engine from stalling. It also stops it from overspeeding.
Okay, during the idling condition, it governors basically avoids the engine to stall, means they will provide the desired amount of the fuel for the combustion.
Mechanical governors in automotive use are called idling and maximum speed governors.
This is a very important point, that the mechanical governors in are generally good for the idling conditions, or when we require, when the engine is operating at the higher fuels, higher powers, or the power range. So that's why these governors are called limiting governors, because the main purpose of these governors are to overcome the undesirable circumstances.
Because idling speed and maximum speed is all they control.
Okay, so idling speed and the maximum speed is all that they control. That's why these governors are called limiting governors. So the question is, what when the engine is not operating on the idling speed or the maximum speed, how the desired amount of the fuel is being injected? So for that purpose, basically your accelerator pedal is also connected to that lever which is operating the fuel rack. So with the help of this accelerator pedal, you basically control the amount of the fuel when you are not operating in the idling and maximum power condition.
They can also be called limiting speed governors. For other throttle positions, the operator determines the rack position by moving the position of the floating link.
So here you can see that this is the accelerator pedal, and this is how we basically control the amount of the fuel for other speed other than the idling and maximum speed conditions. Okay, next, this is the pneumatic governors example, pneumatic governors video. So I will first discuss the details regarding this pneumatic governor, then move towards the video. So this is the typical schematic of the pneumatic governor. Here you can see what are the important things which here needs to understand is that we have a diaphragm unit in these pneumatic governors, and these governors, as the name suggests, are being operated pneumatically. But whenever you see a word pneumatic, means we have something is being actuated, anything is being actuated by the air. So here the pneumatic governors, air is basically operating the amount of the is basically operating the diaphragm compressions and the compression, and when the diaphragm comes back to its original position, this is what these the air is controlling. So the amount of a vacuum, what happens here is that this is our diaphragm unit, and here you can see this is the diaphragm, and here we have a spring which is called a diaphragm spring. So what will happen here is that during the idling conditions in this Venturi unit, this Venturi unit is slightly open. In fact, you can say that this valve, this butterfly valve, is slightly open, so the lesser amount of the fuel would be going into the engine, and because of this, the fuel is also very small. But during the idling condition, we basically require the larger amount of the fuel. So what happens here is we basically have an auxiliary nozzle here as well, and because of this auxiliary nozzle, we have a vacuum. We basically generate a vacuum with the help of this vacuum pipe inside this channel. And when the vacuum is generated, this diaphragm will move against the spring force, and thus it will control the fuel rack and would deliver the desired amount of the fuel in the combustion chambers. This is how these pneumatic governors usually operates. So the amount of a vacuum applied to the diaphragm is controlled by the accelerator pedal, because when you have started the car, this accelerator pedal is pressed very in very small amount, and this butterfly valve is almost closed, is just slightly opened, and the air is going into the intake manifold, which is not good enough for the desired air fuel ratio which is required during the idling condition. So what will happen here is, because of this, since we have an auxiliary venturi in these pneumatic governors as well, and with the help of this vacuum pipe, vacuum is generated inside this chamber, inside this diaphragm unit, and this diaphragm will move against the spring, thus controlling the fuel rack and delivering the desired amount of the fuel into the combustion chamber. So accelerator pedal is basically controlling the vacuum inside this diaphragm unit through the position of the butterfly valve in the venturi unit, because the butterfly valve in this venturi unit is just slightly open and is not good enough for the desired amount of the fuel. This diaphragm is connected with the fuel pump control rack. The position of the accelerator pedal also determines the position of the pump control rack, and hence the amount of the fuel injected. So this is all about the pneumatic governors. Now in fact, this is all about the injection pump governors. We discussed the two different types of governors, mechanical governor and the pneumatic governor. Okay, just one more thing which is being left. I will show you the video of this pneumatic governor. So here you can see this is the diaphragm spring which I was talking about, and this whole assembly would be a diaphragm unit. Here you can see this black color material. Here you can see this is your diaphragm. It's just like a rubber.
A pneumatic governor has a manifold mounted Venturi unit linked by tubing to a sealed
This is your diaphragm.
diaphragm assembly.
I'm just repeating it again.
A pneumatic governor has a manifold mounted Venturi unit linked by tubing to a sealed diaphragm assembly on the inline injection pump housing.
So this is your complete diaphragm unit. We have this diaphragm spring, this is our diaphragm, and it is basically, this unit is basically controlling the fuel rack.
This Venturi unit has a main Venturi and an auxiliary one.
So this is the auxiliary Venturi which I was talking about. When we have a lower speeds, the amount of the air would be passing through this auxiliary Venturi, and it will create the vacuum inside this diaphragm unit, and because of the presence of the vacuum inside this unit, this diaphragm will move against the spring, and it will control the fuel rack as well, thus delivering the desired amount of the fuel during the idling conditions. And when you press the accelerator pedal, and this butterfly valve will be opened, and more amount of the fuel will go through the main Venturi instead of this auxiliary Venturi. So the vacuum inside this diaphragm unit would no longer be here, and the spring will bring back the diaphragm into its original position, and the control rack into the desired position as well.
A throttle butterfly controls airflow through the Venturi and into the engine. The Venturi is narrow and shaped so the air speeds up as it passes through. A similar effect occurs around aircraft wings. The shape of the wing section speeds up the airflow over the top of the wing and creates a low pressure area there, lower than the atmospheric pressure below. The result is an upward force that provides lift for the aircraft. The shape of the Venturi is designed to apply the same principle. When the engine is not running, the diaphragm spring pushes the diaphragm and fuel control rack towards the full fuel position.
So here you can see this diaphragm will come back, and this rack will be in the full fuel position, and would be giving larger amount of the fuel, when desired during the idling condition.
With the engine running at idle, the throttle butterfly is almost closing the intake, and air flows through the auxiliary Venturi at high velocity. This produces low pressure there, which is transferred through the connecting hose to the sealed chamber on the spring side of the diaphragm. Atmospheric pressure on the pump side now forces the diaphragm and rack towards the no fuel position. This reduces the effective pump stroke and the amount of fuel injected. Depressing the accelerator allows more air to enter the engine, but decreases the air velocity through the auxiliary Venturi. Pressure in the sealed chamber rises and allows the spring to move the diaphragm and control rack against atmospheric pressure to increase the fuel delivered. The diaphragm position at any given time is determined by the air velocity through the auxiliary Venturi in accordance with engine speed and load.
See, okay. So this position of the diaphragm is basically dependent upon the air velocity and the amount of the air which is being passing through this main velocity, and this diaphragm is basically controlling the amount of the fuel rack, and thus controlling the amount of the fuel which is being injected into the combustion chamber.
This provides a rack setting which allows the correct quantity of fuel to be injected to match the operating condition.
So okay, that's it about the governors. Now I hope it is all of you must have understand the basic phenomena. Now we will start off with the fourth and final component of the injection system, and that is of the fuel injector assembly. Okay, now I'm going to start off with the fourth uh, one of the most important component of the mechanical injection system, and it is of the fuel injector. So we will discuss about the basic components and the working principles of the fuel injector, and I will explain you the details that how these injectors not only injects the fuel but also helps it to atomize as well, so that we can have a mixture which is more close to a homogeneous mixture and a proper combustion occurs. So what the fuel in so the first question which arrives is basically what is the purpose or what is the function of the fuel injector. So you can simply say that the function of a fuel injector is basically not only to inject but also to atomize the fuel. So how does it atomize the fuel? I will explain this part later. Now moving forward, so here you can see we have a schematic of a fuel injector, and here you can see some of the components. uh, Here you can see that we have a spring, and this is a fuel inlet section. This is from this point the fuel will come into the fuel injector from the fuel injection pump. This entire component is basically the injector body, and this lower component where we can see these nozzle valves as well, this is the nozzle body. So an injector consists of two main components, that is two parts, and that is first one is the injector body and the second one is the nozzle body. Injector body is that body which contains of a spring and the adjusting screw along with the fuel inlet supply line, and the second component is of the nozzle body, which consists of that nozzle valve and the from where the fuel will enter into the combustion chamber. So here you can see that here you can see that we have this adjusting screw and the lock nut. The purpose of this adjusting screw and lock nut is to adjust the spring forces which will act on this nozzle valve. Okay, so for example, if we have an injector, and because of with the passage of time our fuel pump is not operating up to the desired pressure, so what we can do is, instead of replacing the fuel pump we can simply adjust these screws to change the pressures at which this nozzle valve will open and close. So by adjusting the screw we can adjust the pressure, the amount of a force which this spring will be exerting. Okay, now you can see I will explain that what will happen here, how these nozzle injectors would work. Here you can see that we have the fuel inlet passage. This is the fuel inlet passage. The fuel will enter from this inlet passage. The fuel will go through this fuel inlet lines and then into this section here. This is a circular section. Okay, since this is a cross section which has been shown here, this is entirely a circular section, and when you slice it into half, you will see it like this. So at this section the fuel will starts to accumulate. Since there is no area which is available for the fuel to flow further, so what will do, this fuel, since this is a pressurized fuel, it will apply the force on this needle, and this needle nozzle valve will move upward and thus compressing the spring. And after that, here you can see that the fuel which is accumulating here, since this nozzle valve has opened now, the fuel will be injected into the combustion chamber. This is how our fuel injectors basically operates. This was the simple working of the fuel injectors. Now moving forward, by atomizing the fuel, the question is why the atomization of the fuel is very important. So the answer to that question is because of since when atomization is very important, because if we do not atomize the fuel would be injected in the form of a drops, and it will not give a proper combustion, and we will not have a mixture which is closer to the homogeneous mixture. And our requirement is that we form a air fuel mixture which is quite closer to the homogeneous mixture. That's why the atomization has a very important role here. So by atomizing the fuel into very fine droplets, it will increase the surface area of the fuel droplets, resulting in better mixing, and it will give you a better combustion as well. So this is what I was talking about, that atomization of a fuel will give you a better mixing. Okay, atomization is done by forcing a fuel through the small orifice under high pressure. So this is the orifice from where the fuel would be injecting into the combustion chamber, and since its diameter is very small, and the fluid which is coming into this which is lifting the nozzle valve is at very high pressure. So when this high pressure fuels passes through this very small orifice, it will get atomized. So you must have seen the similar effect if you have a garden in your home and you have a rubber pipe which we commonly have in our houses, and when you turn on your tap, the water will come and water will start flowing from that pipe. But if you put a thumb or a finger over it, so what will happen, it will increase the pressure, because you have reduced the diameter, reduce the area which is available for the water to come out. So this is what is happening here. It will not only atomize, it will atomize the fuel, this orifice will atomize the fuel, and as a result of the atomization we will have a better mixing because of these fuel injectors. So the injector assembly consists of a needle valve. This needle valve is basically your nozzle valve. Nozzle valves are type of a needle. A nozzle valve is basically the name of this valve, and needle valve is the type of the valve which we are incorporating in the fuel injectors. Next we have the compression spring, which is mentioned here. So it will lift. Now there will be some resisting force in the spring, and when this fuel which is coming from this fuel inlet has stopped coming, this spring will again push the nozzle valve back to its seat, and no further fuel would be entering into the combustion chamber now. So these are the compression springs. Then we have a nozzle which is atomizing the fuel, and an injector body. So these are the four components. Which fuel injector comprises of. So now moving forward, I have already explained the working of the fuel injector. I will briefly discuss this working again. When a fuel is supplied by the injection pump, it exerts sufficient force against the spring to lift the nozzle valve. Fuel is sprayed into the combustion chamber in a finely atomized fuel. The fuel from this inlet passage will accumulate here, and it will apply the sufficient amount of a force so that this needle valve gets opened, and then this fuel will be injected into the combustion chamber. After fuel from the delivery pump gets injected, when this fuel from the injection pump has cut off, this spring will apply the force, resisting force, and it will bring the nozzle valve back to its original position. This is very important point which I am going to discuss now. For proper lubrication between these moving components, here you can see that we have the small passages here. Okay, here you can see that we have these small passages here, and between these passages this fuel which is coming from fuel inlet will be flowing, and it will work as a lubricant between these moving components. And when it gets into this section, into this spring component section, here this fuel would then leak off, will pass through this leak off passage valve into the section where this fuel can be reused into the or being pressurized again. So this is also very important point. So the lubrication here between this moving component is done by the fuel itself. Okay, so here you can see that a small quantity of a fuel is allowed to leak through the clearance between them and then drained back to the fuel tank. Then it will go back to the fuel tank through the leak off connection, and then we can use that fuel again for the combustion as well. The spring tension and hence the valve opening pressure is controlled by adjusting the screw provided at the top, and I have already mentioned this part, that with the help of this adjusting screw and lock nut we can adjust the amount of the force which this spring will be exerting on the nozzle valve. So for example, if we use a pump which is producing a lesser pressure, what we can do is we can simply unscrew maybe one or two threads of the screw, so it will reduce the amount of the force which this spring is basically resisting, and thus your valve would be opening at the lower pressures as well. Similarly, if we have a pump which is operating at some higher pressure than the design pressure of this fuel injector, we can adjust this screw or tight this screw, and then so the amount of a force which this spring will exert will increase, and this nozzle valve will open at the high pressure. So in that case we can utilize the pump which is a bit which operates at a bit higher pressure as well. So this is how nozzles, fuel injectors and fuel injector, we basically discuss the components of the fuel injector and the working of the fuel injector so far. Now moving forward, now I am going to discuss that part of the fuel injector which is called nozzle. So as I mentioned earlier, nozzle is a separate part of the fuel injector and it has a very important role. Now we will discuss the phenomena which this nozzle is basically utilized for. Nozzle is that part of an injector through which the liquid fuel is sprayed into the combustion chamber. Here I mentioned that this component is our nozzle, because from here this is our nozzle. This entire component is our nozzle, and from this component fuel is injected into the combustion chamber. The nozzles should fulfill the following operation. Number 1, atomization. As I mentioned earlier, that fuel should be atomized for the better mixing, and fuel is coming at a quite high pressure, so it is very important that we atomize this fuel in order to have a proper mixing, in order to have a better mixing. So this is a very important function, since it is a first phase in obtaining a proper mixture of the fuel and air in the combustion chamber. So a nozzle should ensure the atomization of the fuel. Okay, now moving forward, second one is the distribution of a fuel. Now we can understand this phenomena. Here you can see that I have mentioned, I have shown, I have drawn a fuel injector and a combustion chamber here. For example, in this combustion chamber, fuel is being distributed like this. Okay, and similarly here at the bottom I am drawing another fuel injector and a combustion chamber, and in this combustion chamber, here you can see that fuel is being sprayed in this pattern. So what is happening here is that here you can see in the first arrangement we can have a better penetration of a fuel, because fuel is not being properly atomized, and some of the portions of this combustion chamber, like I am highlighting those portions, like this portion and these portions, would not get the amount of a fuel, so that the air in these locations will combust. Since fuel is not sprayed properly, the fuel is in the form of maybe some drops as well. It will penetrate across this dense air and will come in contact with the air which is at the bottom, and not only that, but it will combust with that air as well. On the other hand, in the second arrangement, you can see fuel is being sprayed uniformly across the cross section of this combustion chamber, and we have a very small amount of that area where the fuel is not being sprayed. What will happen here is since the fuel is being atomized properly and and being sprayed across the combustion chamber, what will happen here is the fuel maybe at reaching up till this section, the fuel gets combusted and the air at the bottom may not get the amount of a fuel for the combustion. So we have to do a trade-off between them. So what will happen here is, if we decrease the size of the orifice, we can increase the spray of the nozzle, and by increasing the pressure of the injection pump, we can penetrate this dense air up to the piston, so that the entire amount of air which has been combusted can be utilized for this purpose. So distribution of a fuel is very important. Distribution of a fuel to the required areas within the combustion chamber. This is also the purpose of the nozzle, that it has to ensure that the fuel is being distributed properly throughout the combustion chamber. What are the factors? Higher the injection pressure, better the dispersion and penetration of the fuel. So this is what I was talking about. When the injection fuel pump is operating at the higher pressures, or we have utilized a pressure or we have utilized an injection pump which operates at the higher pressure, it will allow the fuel to penetrate across the combustion or across the area which is being available above the piston. So if the density of the compressed air in the combustion chamber is high, the resistance to the movement of the droplet is higher and the dispersion of the fuel is better. More compression area, this point represents that air density would be higher when we have compressed the air, when we have utilized the larger compression ratios. So when we have higher compression ratios, what will happen here is air has become quite dense, and it will provide the resistance against the penetration of this fuel, and it will give a better dispersion. Higher compression ratios will give the better dispersion across the combustion chamber, but it will not allow the fuel to penetrate across. It will not allow the fuel to penetrate that much across the combustion chamber because of the presence of this highly dense compressed air. Okay, next we have the physical properties of the fuel. For example, when we have a very highly viscous fuel, then atomization of highly viscous fuel is a bit difficult, and their vapor pressures and self-ignition temperatures also play a very vital role here. Next is the prevention of impingement on walls. A nozzle has to ensure that we do not have any amount of a fuel which will locate or which will accommodate across the walls of the combustion chamber. Okay, so a nozzle has to ensure that. What will happen if we have such scenario? For example, if some drops of the fuel has been sprayed across the walls of this combustion chamber, what will happen here is, since the combustion chambers are usually, the temperature of the engines are usually very high, and when this fuel gets in contact with the walls of this combustion chamber, and because of this high pressure, instead of getting combusted, it will break down, and the carbon deposits will start sticking across the walls of this combustion chamber. So your combustion chamber may get the carbon on the walls, and because of the presence of this carbon, the life of the combustion chamber may get reduced. So this is So your nozzle has to ensure that as well, that no amount of the fuel is being impinged on the walls. Prevention of fuel from impinging directly on the walls of the combustion chamber or piston. This is necessary because fuel striking the wall decomposes and produces carbon deposits. Instead of getting combusted, it will get decomposed and carbon will be deposited on the walls of this combustion chamber. This causes smoky exhaust as well as increase in fuel consumption. Next is the mixing. The better atomization will give the proper mixing, and we can have a proper combustion in that as a result. So mixing of a fuel and air in case of non-turbulent type of a combustion chamber should be taken care of by the nozzle. So your nozzle has to ensure that whatever the type of a combustion chamber an IC engine has incorporated, a better atomization can always result in the better mixing as well. Next, we have this topic of the different types of nozzles. Okay, what will happen here is we have here, you can see that we have 4 different types of nozzles: pintle nozzle, single hole nozzle, multi-hole nozzle, and Pintox nozzle. Moving forward, when we are talking about a pintle nozzle, what will happen in these pintle nozzle is, here you can see this shape of the nozzle is just like a thumb pins, and because of its shape, these nozzles are called pintle nozzles. Here you can see that the second one is the single hole nozzle. So this is the schematic of a pintle nozzle, and this one is the schematic of a single hole nozzle. So here you can see that in these pintle nozzles, the cone angles are usually quite higher. So because of these cone angles, a larger surface areas would be covered, of the combustion chamber would be covered. And in these single hole nozzle, you can see that we have lesser cone angles, and so lesser amount of a surface area would be covered by these nozzles when they are spraying the fuel. So this is the main difference between these pintle nozzles and single hole nozzles. So the stem of the nozzle valve is extended to form a pin or pintle. So that's what I mentioned earlier, that the shape of these type of nozzles is basically just like a pin. That's why these nozzles are called pintle nozzles. It provides a spray operating at low injection pressures of about 8 to 10 megapascals. And as I already mentioned earlier, that cone angles of these pintle nozzles are quite high, and they are generally about 60 degrees. So what are the advantages? It avoids weak injection because of these higher spray cone angles. And not only it will avoid the weak injection, it also avoids the dribbling as well. And I mentioned earlier about the dribbling as well, that what is dribbling? Dribbling is basically, for example, if you have a tap in your home, at your home, and it is an old tap, you can see that even if you have closed the tap, some amount of the water will still drop from this tap. This is basically called dribbling. So when this nozzle valve has closed, pintle nozzles usually do not allow the fuel to get into the combustion chamber, while this problem is very common in single hole nozzles. Similarly, it also prevents the carbon deposition on the nozzle hole as well. Moving forward towards the next type, which I have somewhat already mentioned by comparing it with the Pintle nozzles. We have a nozzle which is at the center of this nozzle body. Here you can see this. It is at the center of the nozzle body, and there is only single hole which is close by the nozzle valve, and when the fuel from the fuel inlet comes here, applies the pressure, this valve will be opened and the fuel would be sprayed. So the size of these hole is usually is in the order of around 0.2 millimeters, and injection pressures are 8 to 10 megapascal, whereas the spray cone angle is of about 15 degree, which is quite smaller than the Pintle nozzles. So these may have some disadvantages as well, as they would not be covering the much portion of the combustion chamber. So the only advantage of these type of a nozzle is that they are very simple in construction and easy to maintain as well. The disadvantage is that they have a tendency to dribble. Their spray angle is too narrow to facilitate the good mixing. I have already mentioned this point, that since these cone angles are very small, so we cannot have a better mixing in these single hole nozzle as compared to the Pintle nozzle. Now moving forward towards the third type, and that is of the multi-hole nozzle. Multi-hole nozzles are just like the single hole nozzle, but instead of having a single hole, we have multiple holes here. Here you can see. So thus this construction, these type of nozzles avoids that defect which the single hole nozzle have, that they would not be covering the entire area of the combustion chamber. So it consists of multiple holes bored in the tip of the nozzle. The number of holes may vary from 4 to 18 depending upon the size of the engine, and their size can be up to around 35 to 200 micrometers. The hole angles are again very small, but since we have a multiple holes, so they would be covering the entire combustion chamber, the entire area of that combustion chamber. Here you can see that they can operate at the higher injection pressures as well. So what are the advantages? So that disadvantage in the single hole nozzle, that we cannot have a good mixing. It will become the advantage that mixing of the fuel with air properly, even when the air speeds are lower. And what are the disadvantages? Here you can see that since we have multiple holes, and you can also see that the diameters of these holes are quite small as well, and because of these very smaller diameters, there is a very higher chance and probability that we may have a clogging in these holes. If we have a low grade fuel, then this probability will be increased the probability of a clogging would be very high as well. So close, and the second advantage is, since we have a very close tolerances, and because of this close tolerances, they are very costly as well. So these are some of the disadvantages of the multi-hole nozzle. Okay, next we have the fourth and the last type of a nozzle, and that is of the Pintox nozzle. This Pintox nozzle is simply just a type of a Pintle nozzle, or you can say a Pintle nozzle along with this. Here we can see that this is the Pintle nozzle, and not only that, we have this auxiliary hole, this auxiliary nozzle as well. Okay, so it is a type of a Pintle nozzle with an auxiliary hole drilled into the nozzle body. So it injects, this auxiliary hole injects a small amount of a fuel through this additional hole. When specifically when we are operating at the lower speeds and the lesser amount of the fuel is going into the combustion chamber, it injects the small amount of a fuel through this additional hole, pilot injection. This hole is also known as the pilot injection. Similarly, you must have seen in the geysers that you have a main burner and a pilot burner. Before starting the main burner, it is preferred that start off with the pilot burner. So again, when you are starting the IC engine, that your main nozzle, this pintle nozzle, would not be providing that much amount of the fuel, and your auxiliary nozzle, this auxiliary hole will help this main nozzle, this pintle nozzle, for the complete combustion directly into the, and this auxiliary hole would be directly injecting into the combustion chamber before the main injection. So the needle valve does not lift fully at lower speed. Since we are operating at lower air speeds, so at these lower speeds our fuel pumps are not operating at the desired amount of a pressure. Therefore the amount of a fuel which is coming here for the injection would not be exerting the desired amount of a pressure, and it would not be opening this nozzle valve. So fuel would not be going into the combustion chamber. And for this auxiliary hole, the opening of this nozzle valve does not matter. It will allow the fuel to go into the combustion chamber for combustion. But once your your IC engine has started operating and more amount of the air is going into the combustion chamber, or you can say then your IC engine is operating at the higher speeds, your injection pumps would pressurize the fuel to the desired amount. This nozzle valves would be opening, and fuel will start getting into the combustion chamber from this main nozzle as well. The needle valve does not lift fully at lower speed, as I mentioned earlier. As I have already explained this part earlier. And most of the fuel is injected through the auxiliary hole when you are operating at the lower speeds, or your engine has just started operating. Your butterfly valve is slightly open, just slightly open, so no lesser amount of the fuels are going. We have a lower speeds of the air, lesser amount of the air is going, and we have lower speed of the airs, and it would not be sufficient enough to lift this nozzle valve up, and no amount of the fuel would be going from this main pintle nozzle. Thus at that point, at that instant, this auxiliary hole will provide the fuel. So what are the advantages? It will give the better starting performances. And what are the disadvantages? Injection characteristics are poorer than the multi-hole nozzle. So we can conclude that when we compare a single hole nozzle and a pintle nozzles are more reliable. And when we are comparing the multi-hole nozzle and the Pintox nozzle, multi-hole nozzles are more reliable as compared to the Pintox nozzle. But the Pintox nozzle gives an advantage of a better cold starting performance. So when your IC engine is operating at a place like where the atmospheric temperatures are quite lower, Pintox nozzle can help in the starting of this IC engine. But if we do not have, usually the IC engines do not have this arrangement. The bigger IC engines usually incorporate these multi-hole nozzles, and for the starting at the lower temperatures, what they do is they basically utilizes different fuel. For example, if it is operating at, usually a diesel engine is operating at a diesel, they will start off with some gas and then shift it to the diesels, and that's how they start the engines they start the IC engines which are being used for the power generation. I had two IC engines in the National Refinery, and there was first one was of the 7.2 megawatt and the other one was of the 4.2 megawatts, and this is what we usually do during the startup. We use gas for the startup, and when the engine has started operating and we shift it towards the shift it at full load for the production of the electricity, we convert it into the diesel. We convert the fuel from the gas to diesel. Okay, and next we have is the spray formation topic, and what we are going to study here is, I'm going to explain these figures. Here you can see that we have a figure A, and the fuel is being injected through this nozzle in the form of a drops, and in this figure B, the fuel, here you can see the fuel has now started forming a stream, and in this figure C you can see the fuel has entered in the form of a stream, and then at a distance L2 this stream has started to break as well into the spray, has started converting into spray. So what is happening, what basically represents these three figures here is that when the fuel injection pressure and this would be your pressure inside the cylinder, or you can say combustion chamber, when the difference between these two pressures, injection pressure and cylinder pressure, is low, the fuel will be injected in the form of a drops, and when this difference in pressure increases, it starts increasing, first it will convert into the stream, then at the further distance from the nozzle, they will start again forming the drops. But when we have a sufficient amount of a differential pressure, difference of pressure between the injection pressure and cylinder pressure, the fuel would be injected in the form of a stream, and at reaching some distance, let's say L2, this stream will break into the spray. So what will happen here is that at the start of the fuel injection, the pressure difference across the orifice is low. This is our orifice, and here you can see that at this point before the orifice we have the injection pressure, and after the orifice we have the cylinder pressure. Therefore single droplets are formed as shown in the figure A, and as the pressure difference increases, a stream of a fuel emerges as shown in figure B. Now further increasing this pressure difference, would increase the length of this stream. The stream encounters aerodynamic resistance from this dense air in the combustion chamber, and breaks this stream into a spray. Here you can see that a stream is being coming out of this injector, and because of the resistance offered by this dense air, this stream will break into a spray. So that is how the spray formation is going to happen. And further increasing the pressure, what will happen? Further increasing the pressure will then produce a wavy stream, and then this stream will break into the spray. And here you can see that the length of that point at which the spray is being formed, or you can say stream has been broken into the spray, has started decreasing. Okay, so as mentioned, as you can see this in the figure D. Now further increasing the pressure, here you can see that this length will start decreasing, and you can see that at this point the spray has started forming. That is, or we can simply say that spray would start coming towards the nozzle, and if we further increases the pressure, that when this spray has reached the orifice of this nozzle, further increasing the pressure difference will allow the spray to disperse across the combustion chamber. So this is usually what happens when you place a thumb in front of a pipe. You can see that the water is being sprayed now. So this is how the spray formation is occurring. With further and further increase in pressure difference, the breakup distance, I will explain what is breakup distance. Breakup distance decreases and the cone angle starts increasing until the apex of the cone practically coincides with the orifice, and further increasing the pressure will obviously increase the angle of the spray formation as well. So one thing is remained here, and that is the breakup length. Breakup length is that point, is the length from this orifice, to that point at which the spray has started forming. So this is the distance, or we can say this is the breakup distance in the spray formation. Now moving forward, if we simply apply the Bernoulli equation across the two ends of the orifice, we can end up with this relation. I will not go into the details that how this relation has occurred. Vf is the velocity of this stream, Cd is the coefficient of discharge of this orifice, P injection is the pressure of injection pressure, or you can say the fuel pressure, which is the pressure of the fuel which is coming from the injection pump. This P cylinder is the pressure inside the combustion chamber. Rho F is the density of the fuel. So usually this Vf is in orders of 400 meter per second, but this is a usual value, not an obvious one that we will always have a value in order of a 400. So this is the relation which we would be using in the numericals as well. And now moving forward, the spray formation from a circular orifice has a denser and compact core surrounded by a cone of a fuel droplets of various sizes and vaporized liquid. So denser and compact core, it means that, for example, if this is the nozzle and we have a circular orifice and a fuel is coming in this is, for example, this is the spray, but in this central section we might have a stream of a fuel, and here we might have some molecules of a fuel, maybe in the vaporized form or maybe in the droplet forms, but there would be a stream of a fuel as well, which is being surrounded by this is the or you can simply say we can use the word of this compact core for this spray. This is the center section of that stream, and surrounded it is being surrounded by the atomized or vaporized molecules of the fuel. So larger droplets provide higher penetration. This is, I have already explained this part earlier. When I was explaining the concept of this injection pressure, I have already explained this part earlier, that when the injection when the fuel molecules have a larger size, they will penetrate across the combustion chamber. They will penetrate even in the presence of the resistance from the dense air molecule as well. But if we have a smaller droplets, we can have a quick mixing, a better dispersion of these smaller droplets of molecules. So these surrounding droplets would be dispersing across the combustion chamber, and this compact core would be penetrating across the combustion chamber to ensure that throughout the combustion chamber we have a mixture which is quite closer to the homogeneous mixture. The diameter of most of the droplet in a fuel spray is less than 5 microns. So the droplet sizes depends upon the various factors. Number one, the mean droplet size increases with the increase in the mean droplet size decreases with the increase in injection pressure. As I mentioned earlier, I have explained this spray formation concept, that the droplet size which is coming out of this orifice would start decreasing when the injection pressure has started increasing. When the difference between the injection pressure and cylinder pressure is low, means that the injection pressure is low, so we will have a larger size of the fuel molecules. But when we have an injection pressure, very high injection pressure, and the difference between the injection pressure and cylinder pressure is very high, then we can simply say that the smaller droplets would be coming out of this orifice. So the mean droplet size decreases with the increase in the injection pressure. Similarly, when we increase the air density usually increases when we increases the compression ratio. When the air density increases, the increment in the air density means that we have a larger molecules available in the lower volume. So these larger molecules will resist the fuel to penetrate across this combustion chamber, and it will not allow the fuel to penetrate. Rather, they will disperse the fuel and will break those fuel particles into the smaller droplets of the fuel. So we can say that by increasing the air density, the droplet size also decreases. Okay, next factor is of the fuel velocity. when the fuel velocity is increased, means the fuel particles are quite close to each other, and they are being attracted with each other. They are joined with each other with larger attractive forces. So it is difficult for these molecules to break into smaller sizes. Thus we can conclude that when the fuel viscosity has increased, the mean droplet size has also increased. The fuel viscosity of the lower grade fuels are usually high, but we do not want these fuel viscosities to be quite high, because they will result in the formation of the fuel molecules which have a larger size, and they will not give the proper combustion, and they will not be providing a better mixing as well. So the last one is by increasing the size of the orifice, means now we are increasing the diameter of an orifice. So as I mentioned that we will have this orifice of a very smaller diameter, because this smaller diameter will disperse the fuel and will atomize the fuel. But if we increase the diameter of this orifice, what will happen is that the fuel will start forming bigger droplets, or we can conclude by saying that the size of the droplet will be increased. So we can conclude this topic of spray formation by saying that the droplet size decreases with the increase in injection pressure, decreases with the increase in air density, increases with the increase in fuel viscosity, or increases with the increase in the size of the orifice. Okay, next we have the topic of a quantity of a fuel and the size of nozzle orifices. We would be using this relation in our numericals. That's why I'm explaining that how this relation has obtained. We will not go into the details of this topic. By the word quantity of a fuel, it simply means that how much amount of the fuel is being injected into the combustion chamber. Similar relation can be used for the size of the orifice as well. That, for example, we require this much amount of a fuel, and in that much in the desired time. So we have some parameters which we already know. Now we can simply calculate that what will be the diameter of the orifice which we would be using to inject the required quantity of the fuel. So the quantity of the fuel injected per cycle depends to a great extent upon the power output of the engine as well. So this is the fuel. The power output is the only primary factor at which the amount of the fuel which is to be injected is dependent on. So it can be calculated that by simply multiplying all the area of the orifices. For example, if we have a multiple 4-cylinder engine, then we have 4 orifices, 4 injectors, and these 4 injectors would have one orifice. So we have 4 orifices in the 4-cylinder engine. But if we have in a larger IC engines, we usually have more than one injector in one cylinder. So we can have more than one orifices in a single cylinder as well. But that is not a case in our automobiles. So usually the preference is on the automobiles as far as this course is concerned. So I will just consider that we have for each cylinder we will have a single injector. Next one is the fuel jet velocity. So by here we can say that this relation is quite much similar to this relation of the continuity equation which you have already studied in the course of thermodynamics, or maybe studying in the course of a fluid mechanics 1 as well. So the next factor here is of the time of injection. this is an important factor, which and it is to be understand here that fuel would not be injecting throughout the operation. Fuel would only be injected at some particular angle of the crankshaft. Let's say that before reaching the top dead center, fuel started injected 10 degrees before reaching the top dead center. Piston is reaching towards top dead center, but before reaching that point, fuel injection has started 10 degrees of the crankshaft rotation. And when the piston reached the top dead center, fuel is still being injected into the combustion chamber. Combustion starts. Piston starts moving downward. Let's say even after the 10 degrees of the crankshaft rotation, from let's say from this 10 degree to this 10 degree of the crankshaft revolution, the fuel has injected. So this 20 degree of the crankshaft is the time duration for which the fuel is injected only, and except that 20 degree of the crankshaft angle, we are not injecting the fuel in the combustion chamber. So this theta is representing that crank angle, and one revolution consists of 360 degree. So for, I assume that for the 20 degree of the crankshaft we have the fuel injection, so it will be 20 upon 360. This 60 is for conversion of this RPM into the seconds. Okay, next factor is of the number of injection per second for one orifice. Next is here we have used this Ni, but in the numericals of chapter 1 you might have used this factor as simply small n as well, and for the 4 stroke it would be n by 2, and for 2 stroke it would be simply n, and this is for 2 stroke engine. So but here I have not used small n. Instead of using small n, I have utilized capital N I. I in the subscript represents the injection, and n represents the number of injection. So why haven't I used the small n? Because I have used this small n for the number of orifices in the first component, first section of this equation. That's why I haven't used small n in this relation. And since we are talking about the number of injections per second, and this capital N I would be in minutes, we will divide it with the 60 to convert it into per seconds. This ends up with the topic of the spray formation and the quantity of a fuel and size of the orifice. We would be using these relations in the numericals, which I will start off in the next class. And in the next class I will also discuss some of the new technologies which are being used as throughout this topic. I mentioned that this fuel injection systems are used in CI engines, but if you look at the modern cars, you have instead of a carburetor we basically have an EFI. I will not discuss the EFI systems yet, as it is not the part of your course curriculum. But I will discuss the brief overview that how we basically utilize these injector systems in our SI engines as well, in replace of the carburetors. So till the next video, okay, Allah Hafiz.